Hey folks, this video is about rotational energy, and so to kind of start you thinking, I have a gyroscope. Now this gyroscope already has like the little ripcord in it. If you've never seen a gyroscope, it's this like plastic. This one's a plastic frame with a metal bar going down the middle and this green disc. And the green disc is like abnormally heavy for the entire size of the gyroscope, and that's pretty important to the gyroscope's motion. But what I want you to understand is this ripcord has like little teeth on it, and those teeth are mimicked in this the end of this green bar right there. And so when I pull, I'm going to pull in this direction, and the ripcord's going to come through, but all the teeth are going to interact with the teeth of the green disc. And when I pull this way, the green disc is going to start to rotate. And so I pull as hard as I can or want, and the green disc starts spinning, and the gyroscope will, well, this one's kind of old and not awesome, but it does some nice gyroscopic things. And so we are going to focus on what happened to get the gyroscope moving. So we are going to imagine a scenario not unlike that. We have a wheel, there's a rope wrapped around the wheel, and that's pulled with force F. We want to imagine that the center of the wheel is fixed somewhere, like maybe it's actually a bike wheel. That I flip my bike over so that it's resting on the handlebars, and the front wheel is like free to rotate. And I like tie a rope to the wheel, and I just pull as hard as I can. And maybe like the rope is made so that it detaches after I pull on it. But I'm just going to examine what happens in terms of a force. So I exert a force along this direction. So that's the direction of the force. Now, the point where the rope kind of leaves the wheel is right there. And so I can draw like a radial line that way. So that's going to be R. And that is also the like initial position of that radial line. Almost imagine like a wheel with spokes. When I start to pull, that radial line starts to rotate with the rest of the wheel. And it's going to rotate through some angle. Now let's just imagine that I managed to pull the rope, and in that time the wheel rotates exactly 1/4 turn. So 90 degrees or pi over 2. What I want you to remember is because of the way circles work, that angular distance is accompanied by an arc length. And so I pull, during the pull force, the wheel rotates through an arc length, or the surface of the wheel travels an arc length equal to S. Now what's also happening is I'm also pulling on that rope, and I pull at a certain distance. So I pull with the force F over some distance. So what I can actually think about is I can think about the work done on the rope. And in this case, I pull the rope this way, and my hand and the rope itself moves in the same direction. So work equals force times distance. Okay, now at that moment the rope leaves, right? Like if I rotate the wheel so that it travels an arc length of S, that spoke travels an arc length of S, well, I've actually pulled that exact amount of rope off of the wheel. So in this situation, that distance D of how far I pull the rope is equal to the arc length that the top of the wheel just rotated. So the work is really F times S. And that might not seem very significant, but now I have the work done on the wheel in terms of the force that I apply and something the wheel did. And so that's kind of handy. Now the wheel rotates through angle theta. So since that arc length equals R theta, I can make a substitution. I can say the work is equal to the force I exert times the radius of the wheel times the angle through which I turn the wheel while I'm pulling. So I mean, I can let go. Like I would have to make sure that when I pulled on this force, once the wheel had rotated that 90 degrees, I like stopped pulling, because that would represent the end of me doing work on the wheel. Last thing is, since torque in this situation is just RF, I get the following situation. So work is equal to torque times angular displacement. So I can use this idea, and this represents rotational work. So by pulling on it with a linear force, I do regular old work on the rope, and the rope, because it's causing a rotation, does rotational work on the wheel. The unit for work is the same no matter what, same unit as energy. And so rotational work is torque times displacement. And so that's kind of useful if you want to understand, did the energy change or not? That's something you can do. So why don't we pick up where we left off with that idea? We have this work-energy relationship. And so if work is done, that means that the energy must have changed. And so work produces a change in the rotational speed, right? So when you pull on the wheel with a certain torque, you pull on that with the force, and now you've caused that wheel to rotate. So that wheel now has angular velocity, and the particles of that wheel, and the wheel's particles, each have a velocity that's tangential, that's equal to r times omega. And so we're just going to play with that. We go and say, okay, so now that everything's rotating, because everything's rotating, all the particles have a linear velocity. So the kinetic energy of a particle is equal to 1/2 mv squared, where the v is the tangential velocity. So that's for a particle. Now, the goal of this next part is to take the particle definition of kinetic energy and ramp it up until we're describing the entire object. So this is the regular old translational kinetic energy for the particle. Now I know that V equals R omega, so in my next line I have 1/2 m times R omega squared. And so this derivation is actually pretty quick. If I break this apart, I now have K equals 1/2 mr squared omega squared. And you will recognize mr squared as a familiar term, and that's moment of inertia. So this is moment of inertia. So the kinetic energy of a particle on a wheel is equal to this, 1/2 mr squared times omega squared. This is in terms of the specific particle, and this is in terms of the entire object. And so if I wanted to ramp that up for the entire wheel, I would have to add up all the kinetic energies of all the particles in the wheel. And when I add up all the mr squareds, I get I. And so the rotational kinetic energy of a spinning object is 1/2 I omega squared. And you'll notice that it has the same format as kinetic energy of translation, 1/2 mv squared. It just has variables that are associated with rotation, also measured in joules. And so, everything that we learned about energy, we can still apply. And if an object is rotating, in addition, it has this other type of energy. And so in our class, we're going to explore how rotational kinetic energy plays into what things do when they roll down ramps. And that's about it for AP Physics 1. So there can be also like a spinning apparatus, but I like to focus on things rolling down ramp, and that's it.